for the introduction, Justice.
Of course.
So the maybe subtitle or elevator pitch description of my talk is building machine learning IoT products is hard, and the Elixir ecosystem can help. And so maybe before I get into a lot of the details, I'll just give a small description of who I am, why am I here. I am new to the Elixir community, definitely. I'm the data science practice lead at Berry, and I come from a more of a traditional data science background, although there are many different paths that people can take into the field of data science. It's pretty common for people to have done, a bunch of analytical degrees, and so I did undergrad, master's, PhD in math stats, electrical engineering, and then worked at a few startups, AI startups in Silicon Valley. And I definitely found that building these types of AI products or products that have a significant machine learning component to them, it can be tricky. And the traditional data science development cycle is pretty different from like an agile software development lifecycle. And so there are a lot of really hard-won best practices that software engineers have developed for product development, especially agile product development, that the data science community can really benefit from. And so that's what brought me to Very, because they have such a strong focus on agile development, and being able to bring that into a machine learning product development process is what I was really interested in. Very, the company itself, is an IoT engineering firm. So customers hire us to build software products for them, most of which have an IoT component of some kind, and many also have some machine learning component as well. We're a fully distributed company, so everyone works remotely. There are no offices. Even pre-COVID, this was true. And very heavy emphasis on full stack agile development. When I say full stack in this context, it's a bit of a fuller stack than we might traditionally talk about. So it's not only kind of front end, back end, and databases. The common extension maybe is into mobile app development as well, but we're also extending into the hardware and firmware side of things, as well as up into the machine learning side of things. And so both of those extensions are areas that are maybe in those fields. People who come from those areas are not as used to more of a agile development process. And so trying to build products that actually extend through this full stack and have a pretty wide range of individuals, people, and skill sets required can be a really fun, interesting process. And so in today's talk, I'm going to be focusing most heavily on the machine learning side of things, as well as how data is actually getting from the hardware and firmware up into the machine learning component. And so that's exactly where Elixir comes in. Oh, and side note, if you want to hear more details on the hardware firmware side of things and the approach we take at Very, one of my coworkers, Dan Lindemann, had a talk right before this, and so definitely check out the video if you missed it already. I should also give credit that this slide I stole from him directly. So today I'll kind of split up the talk into two components. One is more what we did, kind of what type of an application was it? What is this kind of industrial IoT thing that we were trying to build? And then the second part, I'll focus more on what did we learn from this process, especially with respect to data science and Elixir developers as data engineers, and how those two kind of teams can interact effectively. So the kind of interesting part about what we did for these purposes is that we built a machine learning IoT product, and that Elixir was I was going to say that a heavy component, but maybe I should say all of the firmware, backend, and data pipeline. And when I get into what we learned, some of the key takeaways will be, one is that people coming from different backgrounds and different disciplines often have different terminology to talk about the same things. And so I'll do a bit of an aside on how data scientists tend to think about data to be able to help with the translation between kind of Elixir land and data science land. And also one of my key takeaways from this experience is that Elixir developers make great data engineers for machine learning products. Named Sun Automation Group. And so what they do is build machines, and they also sell and service machines that other companies build. And what these particular machines do is make cardboard boxes. So it's the corrugated industry, as it's called. We're pretty lucky that this industry is doing well under the current circumstances. There's no shortage of requirements for cardboard boxes these days with all the shipping that's going on. And so the question was, if we have kind of a big machine like this, how can we turn it into like a smart machine? There's a lot of talk and buzz in industrial applications right now with like Industry 4.0 and whatnot. And so what was imagined is, some type of UI that like an operator could look at, and they could see all the data flowing from the different sensors on the device. They could understand the status of the device really easily, see the different sensor readings, and also get alerts if anything looks bad or unusual. And so in kind of machine learning lingo, we call this anomaly detection, when it's kind of alerting to something unusual happening. And then the next step would be adding in things like predictions or recommendations about when the system might be about to head into a bad state, or if there are parts that need to be replaced. And so the first part that we've already built that's out in beta mode is focusing on the anomaly detection aspect of the system. And so one other thing maybe to mention about these type of big industrial machines is that they already have a PLC, a programmable logic controller. It's like a little kind of rugged computer that the machine is already talking to. And so it's reading data already kind of from the various sensors. And often it's just being used to make programmatic adjustments. So, operators can say, set this piece to this height or put the temperature at this level. And it's kind of a basic control loop type of controlling of the system. So if they see that the temperature, if the PLC sees that the temperature is, falling below the set point, then, it turns the heater back on for a bit, or whatever the mechanism is. And so the data is already flowing kind of into and through the PLC, but it's not typically sending it anywhere for further processing or analysis, or kind of doing any fancy predictions or anything like that. And so what we wanted to be able to do is take that data streaming through the PLC, grab it, send it up to the cloud, and then build a product that makes that data more accessible and usable and allows you to make statements off of it. And so here's the kind of cartoon simplified version of what we did. This is meant to represent, here we have our device, our machine in the factory, and we have the PLC, which we have firmware on the PLC in Elixir using nerves. And so that's kind of the first place that Elixir enters our system. And so grabs the data, streams it up over cellular into AWS IoT core. We use AWS pretty heavily. Everything pretty much after you get off of the firmware itself lives in AWS for us. And AWS IoT Core is just one of their tools that's built for kind of handling streaming sensor data from IoT devices. From there, it gets dumped into a SQS. This is Amazon's Simple Queue service, and comes into our Elixir backend, which is, we use the Phoenix framework for that. And so then we begin some kind of per message processing, which uses Broadway. Inside that, we are you can think of each message as like a list of all of the kind of key value pairs that we're receiving for each second, where there's like, this is the sensor, this is the value, this is the sensor, this is the value. So it's like a list of 2,000 key value pairs representing what all of the sensors are reading at that kind of 1 second in time. And then from that message, we're also computing some derived variables. And so things that are not getting measured, directly by the sensors or the PLC, but you can compute off of it, like measures of throughput, for example. And then we're also pinging the anomaly detection data through after we've kind of appended on all of these derived variables and anomaly scores along into the front end via WebSocket. And then at the same time, we use batch processing to be able to store it to the database, and longer term storage in S3, which the machine learning model will be built off of. Everything on the machine learning side is done. We use Python and make heavy use of some of the AWS services like Lambda, API Gateway, and SageMaker for the machine learning side of things. And then I should also mention that Ecto is what we're using for the database side. So we're using it to set up all of our entities like machines and anomalies and issues and facilities and customers, and giving API access to all of that from the front end. In terms of tooling, our front end is based on React and also uses Redux and Redux Saga. And then at the end of all of it, we have our end users who actually have a UI, and they're able to get alerts about issues and anomalies, go in, look at analytics on historical data for a given machine. And then also there's like kind of super users who care about what's going on across maybe like a fleet of machines and can see some summary information about that. And so why was Elixir so helpful and so important for this? Number one, developers like to use it. It's fast, computationally, and like in terms of handling a lot of data flowing through, but it's also, great to use as a developer. And also we have a lot of async data processing going on where we're wanting to be handling individual messages and updating information about them as they go through. If we were not using Elixir, probably we would have needed to do the firmware development in C or C++. And so this is really likely going to be adding more people and more kind of skill sets and technical stacks required in the process. And the backend maybe would have been Ruby on Rails or Java. And so, as I mentioned earlier, when you have this kind of very tall stack that you're trying to do agile development on, the more that you can have people who can like reach between components of the stack and work on multiple pieces, the better, because then it reduces the number of places where you can kind of have miscommunications. And so what did we learn as we were going through this? Terminology can be really important. So I'm going to spend a few minutes talking about how data scientists think about data. And some of our conclusions are going to be, when I say the word model, that's probably pretty different than what you're thinking of when you say the word model. I might talk about something like an observation, or maybe I'll talk about a row in a table, or I'll talk about an entity even. And you might use words like a schema, or actually a model, or even a struct or a map to talk about those things. And some of the ways that we tend to think about data handling in a sync versus async way can be a little bit different as well. I won't spend as much time talking about kind of agile development, but I'll circle back to it a little bit at the end because it's really important. And so I just want to kind of emphasize some of the characteristics of agile development that still really apply in this kind of extended full stack development process. So how do data scientists think about data? We want to build models. And when I say model, I'm talking about something that is like a box that can take in an input and give back an output. The input could be something, could be a single variable, potentially if it's a super simple model, but typically it's something that's like very much higher dimensional. So you could have tens or dozens or hundreds of variables. Y, on the other hand, could be one, or it could be more variables. So how do we get a model like this? There's a lot of ways. For example, if it's a discipline like in physics or something like that, a lot of the time you might actually have a physical understanding of the system and what's going on, and have equations that already relate inputs and outputs to each other. And so in that case, you don't need to necessarily learn anything from the data, but you already know the differential equations or whatever that govern the physical process, and you can use that model to pretty accurately describe the state of a system and predict what some outputs are going to be given some inputs. Or similarly, if you have maybe some type of business process and a rule-based set of like decisions that someone understands as like a business user, then you could encode those, in code, and have some type of model that's again not based off of learning something from the data, but based off of like someone explained how it worked, and then you encoded it so that you can get the right relationship between inputs and outputs. And so I would say like the maybe defining characteristic of machine learning is that instead of already kind of a priori being able to say what the relationship between inputs and outputs should be, machine learning models work by, you have to just give them a whole bunch of examples, lots and lots and lots of already matched together. For this X, you get this Y. For this X, you get this Y. For this X, you get this Y. And after seeing enough of those, it can now take new X's that it's never seen before and make a pretty reasonable guess for what it thinks the Y is going to be. And so this process of giving a whole bunch of examples and getting back this trained model, as we call it, it actually requires a couple of inputs into this model training process. And so we have the data that I was just mentioning, which is all of these pairs of X's and Y's. This is a big kind of historical data set. But then we also need to tell it what model type are we trying to train here. So for example, if you're trying to train a deep learning model, maybe you're going to say this is a convolutional neural net, or this is a variational autoencoder. Or if you're not using deep learning, if you're using like a random forest is a good example of an ensemble tree-based method. There's dozens, maybe hundreds of different types of models, and some are appropriate in different types of circumstances. So you need to say specifically, okay, this is the exact type of model that we're going to use. And then also each model has often a lot of hyperparameters associated with it. So, how many trees are going to be in my random forest, or how many, layers should my neural network have? What's my batch size going to be? What should my learning rate be for the optimization function, etc. So once you choose model type and all of the hyperparameters for that model, then you can give that model a whole bunch of data, go through this kind of model training process, and then come out with this trained model on the other side. And so in practice, a lot of the time, if you hear a data scientist talk about hyperparameter tuning or a model selection or model validation process, often they're going to go through this entire thing many, many times. And so they might be putting in different options for the hyperparameters. And then for each combination, you get out a trained model. And then what you want to do is have a new set of data, like we call it a test set. And so your training set is the one that you use for model training. And then you have another test set where you have the X's and Y's already matched up, but you're just inputting the X's into your trained model. And then you're getting whatever predicted y's the model is outputting, and then you're comparing those to your known actual y's, so that then you can kind of see how good the performance is of the predictions from the model. And so you go through this thing a whole bunch of times for different model types or hyperparameters, and then you can at the end say, okay, this is the best one out of this suite of ones that I tried. And so I say all of this, I'll come back to my kind of initial point, which is how do data scientists think about data? And so here, this kind of set of X's and Y's that we use for training data is generally structured in the form of like a table. So we'll often call this a data frame or a matrix or like an array, a 2D or n-dimensional array. But you can think of it as like a database table or an Excel spreadsheet style type of data. And so when we have one of these kind of entities, this database for data, you can think about each row in the database is one observation. And so an observation is the thing that we are trying to do modeling about, the thing that we want to be able to make statements about. And so it might have many, many attributes. And so we'll typically call these attributes features or variables. And so in Ecto, this observation is what you would refer to as a schema or like a model in the MVC mindset. And if you're talking about like the actual data type of how observations are typically stored, you would probably call it a struct or a map. And then it'll often just be written as rows in a database table. And so in the case of where you're trying to do predictive modeling, that means that each observation actually has some characteristic associated with it that is like a special one that you want to be able to predict or make statements about. And so typically this kind of outcome variable or a set of variables, they're not going to be actually available about the observation at the time when you're making a prediction. But what is available are a bunch of other attributes. And so these are like our X variables or attributes. And so for the historical data, it's important that you have both the X's and the known Y's, the known outcomes, and that those are all kind of associated with individual observations. But then at the time that you're making the prediction, you typically only have the X attributes and you're trying to make a statement about what you think Y is going to be. And so when you have a whole bunch of observations of these kind of X's and Y's already matched up, you often will store them like in a great big database table. And then this is what we use as kind of input into our model training process. And so one important note to call out here is that a model that has already been trained, we chose already pretty specifically that this is the structure of data that it is designed to accept. This is the specific attributes of each observation that need to be given as input. And then this is the specific kind of attributes or outcome variables that we are making statements or predictions about. So I want to make it a little bit more concrete by walking through just a little example that might help make things more intuitive. So say that we have data that kind of looks something like this. So for each observation, we have two kind of attributes that are input variables. So these are like actual X and Y coordinates. And so let's say our outcome variable is this Z coordinate as represented in this kind of little surface here. And in this example, let's say that the X and Y coordinates are actual like geographic location, and that the Z coordinate, instead of representing like elevation or something like that, represents the housing price of a house at that geographic location. And so, you can see there's definitely a correlation between location and price. We know that this exists in the real world, that housing in one area is maybe generally more expensive as compared to another area. And then maybe what we're seeing here is actually like a smoothed version of the relationship between location and price. And so for individual houses, they wouldn't lie exactly on this surface. Maybe they would be, some would be above, some would be below, etc. And so real data would be, we would call it a bit noisier than this. And really that is what we mean when we say that there is noise in a data set, that there are some additional sources of variability to the outcome that aren't explained by our input variables. So in this example, it's like there's more to a house price than just the location, even though location is clearly really important. And so then if we wanted to actually improve the model, we could add some of the other variables that help explain this additional variability in housing price. And so this could be things like, unit type, or how many square feet the unit is, or the lot size, number of bedrooms, bathrooms, how recently it's been renovated, some of this type of information. And so if you are someone like who wants to be able to appraise houses for tax purposes or something like this, then this type of model might be super helpful for you, because you can take a whole bunch of characteristics about the house and the location and then get a price estimate. And so on the other hand, if you're someone who maybe owns a house and wanted to sell it, then this type of a model, it would be a little bit helpful for you. Like, it gives you kind of a general idea of, if you put all this information about your house into it, it tells you what your kind of maybe recommended price would be. But it doesn't really give you anything to control, or like, it doesn't help you make a decision necessarily. Say, if, for example, if you're in a rush that you want to sell quickly, you know that you need to price a bit lower probably than this recommended price, but it doesn't really tell you anything about the relationship between price and how quickly you're going to sell it. And so if you wanted to actually have a model that did that, maybe the thing that you want to predict is not housing price, but something like days until sold, or even you could want to predict something like probability of selling within the next 30 days or next 90 days. And so in that case, price would actually be one of the characteristics that you're using as an input variable into a model like that. And you're saying, if I price it like this, it would probably sell this quickly. If I price it like that, it would probably sell that quickly. And so the same types of other variables like location or property characteristics would probably be helpful as other characteristics in that model. But you might also want to be able to consider even more additional characteristics. So for example, what time of year is it? Like, how is the market doing right now? Other similar properties, how quickly have they been selling, for example? And so the types of kind of additional data that you would want to do add on to that model is going to vary depending on kind of who your like end user is and what types of decisions they need to be making off of the data. So I think this is actually one of the biggest jobs of a data scientist. Maybe this is even like a majority of the data science process is I call it analytical framing. I'm not sure of a better term for it, but it's really like, okay, we have some vague, maybe ambiguously framed business problem. Like in this case, it's something about, we want to know what the price of a house should be. But if you frame it one way versus if you frame it the other way, not only are you making different statements, like this is my expected house price, or this is my expected number of days until sold, given a price and a bunch of other factors, but you also, like, the actual data that you need and the way that you structure it is going to be really different. Like, what each observation represents is no longer just a house, but it's a house at a point in time with a bunch of other market context. And so this process of analytical framing is really like, what is this observation? What is this row level entity that I'm trying to model, making a decision about that? And as well as kind of what the specific outcomes that we're trying to predict are, and what the other attributes, the information that we want to use as inputs to the model should be. And then the field of machine learning really comes in once you already have your data, like you've done the analytical framing, maybe you've had to do a whole bunch of transformations, aggregations, etc., to be able to get whatever raw data sources you had into this model-ready format. And that part is typically where Elixir developers can come in to the process and be really helpful, is helping data scientists go from that raw data into this aggregated form. But once you have that kind of all set up nicely, then what machine learning is about is really like, given this input data, what we're trying to judge is how to kind of tell the difference between different observations. So like, what is the right notion of similarity or like distance between observations? And so, for example, here, like if you have the location of a house and the price of a house, and then you know that there's another house that's 2 blocks away and you want to guess something about the price of it. You know, if you go 2 blocks in one direction, maybe the price is really stable, but 2 blocks in a different direction and suddenly things get really expensive. And so machine learning model, it's not going to just say, okay, take my X and Y coordinates and look at the exact distance between them. It's going to learn like, what is the right combination of your X and Y coordinates, and then all of these other variables together, to be able to actually get the most important information to be able to make an accurate prediction about the outcome that you're trying to predict. So I would say majority of data science is kind of analytical framing and being able to get the data into the format that you need for actual modeling. And then machine learning, which is kind of one part of data science, is really about, once you have that training data, using the best methods that you can to be able to kind of clearly distinguish between observations that have similar outcomes and observations that have different outcomes. And so kind of circling back to the context of like building a production machine learning product, we kind of have a few different paradigms that we work in. So I mentioned there's this kind of analytical framing part of it. And this is something that you would love to get right from the beginning, because so much depends on it. When you make changes to the way that you're analytically framing the problem, these are often breaking changes with respect to like a software system, because you're changing the definition of your input and output requirements. And so this is one of the reasons that it's actually super useful for people who are working on the data flow and the data scientists to be working together really collaboratively all the way from the start. Because I'll get into it more in a second, but there's a lot of decisions that you can make about what data should be handled where, especially when you have raw data coming in, and then you have a whole bunch of different derived variables that you end up using for machine learning, but you might also be using them for other parts of the system. And so making decisions about like, what exactly is getting computed in the back end, maybe by Elixir developers, what exactly is getting computed maybe off in the machine learning pipeline somewhere, and then what data is being kind of passed to and from those components of the system. Because especially when you're doing kind of greenfield development of new products that have this kind of machine learning component to them, it is actually really common for the details of the analytical framing to change and adapt over time, because the developers and often also kind of the business subject matter experts were all often gaining like a better understanding of the data, of the system, of the end users. And this is why we want to follow like an agile development process. So I should next say that beyond this analytical framing piece, which you can tell I place a lot of emphasis on, there's kind of two different modes of the actual machine learning side of things. There's the model training aspect, and then there's the model inference aspect when you already have a trained model and you're just kind of pinging it with the data that's flowing through the system. And so for model training, this is where you need all of the historical data with already the matched inputs and outputs. And so this is often done kind of offline or in batch. there do exist kind of online model retraining processes, but a lot of the time you do see offline model training. And so all of those derived features, they can be computed synchronously a lot of the time. And so this can also be a point of miscommunication sometimes, because data scientists tend to use a lot of derived variables that are actually maybe difficult to compute asynchronously or live. And so then, for example, if you want to be able to standardize some data, it's a really common practice where you take the variable and you divide it by kind of the mean based off of that variable historically. And so if we want that type of standardization to be done on like new data that's flowing live through the system, then we need to be kind of storing what the mean is that we're dividing by. And if that computation is being done in the back end as opposed to kind of in a separate machine learning pipeline, we need to be able to pass that information on where it needs to be computed. And so then there's this kind of final piece of the process, which is the model inference stage. And so this is typically when you have actual live data flowing through the system and you're querying this trained model and getting a prediction back. And so sometimes you do this in batch, but often it will need to be done in kind of real-ish time. And so a key kind of decision point here between our backend developers and machine learning developers or data scientists is really like, what exactly is this interface need to be? And if there's a difference between the data that's flowing into the system and the kind of model ready data that needs to be kind of pinged, then where exactly do we want those computations to happen? Usually we don't want the same computations to be happening in like different code bases for different places. And so especially when you're computing, it's often called feature engineering, this process of creating these derived variables from the raw data. And a lot of the time you actually, in machine learning systems, or even any type of like data heavy application, a lot of these derived variables, they're helpful to the machine learning model because they're also relevant from a business context. And so it's nice for the end users in many cases to be able to see a lot of those derived variables. And so that's one reason why you would want to consider having them be computed actually in the backend on the live data as it's flowing through. If it's something that's not as relevant for the end users and doesn't need to be surfaced in other parts of the application, then it's in some ways almost easier, because maybe we can make the contract between the machine learning pipeline and the backend can be based off of just the raw data. And in that case, you don't really have to care what's going on from a feature engineering perspective. You pass it the raw data in terms of like the long-term storage, like the data that it's doing the training off of is going to be in the raw format. And then the machine learning pipeline will take care of all of the transformations it needs to do before training. And then at the same time, when you're actually pinging it data to be able to compute, make predictions off of, it's going to also handle all of the transformations or whatever it needs to do to be able to convert it into this type of format that the model accepts, knows that it needs to take in. And so I guess all of this to say that try and be as clear about interfaces as possible at each point in time. I think that often we can get into kind of confusing states where we know that we're writing a bunch of data to the back end and that the machine learning models are kind of using it in some way. But we're not necessarily always explicit about, these are the characteristics of the data that I expect in this way, and they need to be kind of written in this way. And then also exactly the format of any APIs, or if we have streaming data coming out of the machine learning pipeline, the format for those, just being really clear about what's being computed where, and having everyone understand enough about the entire system and the final product and what the end users need, that we can be kind of collaborative and intelligent about making these decisions and these trade-offs about what to be computing where. One thing that I feel like is maybe relevant here, although I don't have it fully thought out, is the concept of domain-driven design. I was reminded just seeing Japaswadi's talk right before this, and I definitely think that domain-driven design is a concept that is not actually used heavily enough in data science. There's not a ton of data scientists who are really familiar with the principles behind domain-driven design, but I think that a lot of the same types of principles apply. Like, what are our entities? What are our observations that we're talking about? So anyone who is kind of an expert in this area and wants to talk to me more about this offline, please ping me because I'm very interested. And so I think I mentioned most of this on the previous slide, but just to call out a couple kind of key considerations when we're serving data for this machine learning system. And the main consideration that we need to make as Elixir developers and data scientists is what information exactly are we passing to each other and who is computing what where. And so when you're making those decisions, the first most important thing is, are the attributes being used other places in the system? And that makes it seem like we should be computing them more in the main part of the backend as opposed to having them computed in the backend for the UI purposes, but then again, computing them separately in the raw data, off of the raw data in the machine learning pipeline. Also, do the derived features depend on any information that needs to be learned from the training data? The example I gave was like, if you need to be normalizing by the mean or something like that. If it's something that you can't compute asynchronously, then this needs to be included in the information that is getting passed between the machine learning system and the rest of the backend. And then another consideration is what the required turnaround time is between like a piece of data flowing into the system and how quickly we need to make the prediction about that data. So that's my really big aside on how data scientists think about data. The main points of it are the word model and the word model are not always used in the same way. I'll often talk about an observation, so you can just think schema or model. And also we tend to think about synchronous versus asynchronous data handling a little bit differently. I won't get into this section really at all, but agile development, I just want to say, still applies for all of this. So if you're working with data scientists who are not really maybe up to speed on DevOps best practices or anything like that, please try and like help encourage them to move in this direction. Try and get everything, up and running end to end as early as possible, even if it's like super simplified, almost like just no-op boxes in each of the different pieces, being able to actually have the data flowing or simulated kind of as close to the point of origin as possible, and then doing the majority of your development on like a working system, as opposed to kind of working in silos and then trying to put all the pieces together and bring it over the fence into production towards the end of things. Be as clear as you can about interfaces. Anytime there's an interface, just try and make it really clear and explicit what you're expecting or what you're providing. Data scientists maybe are not as good at this as software engineers are on average. So if you have any data scientists in your life, try and help them move in this direction. And of course, just kind of be always making frequent small updates and have that be the main way that you work. That's everything that I had for today. I really appreciate all of you coming. And I should also mention that we're hiring. So please check out verypossible.com/careers if you fit into any of these categories listed here. I hope that I left enough time. I think we have about 5 minutes maybe for questions. So I'll try and pull up this list of questions in the app. Okay, let me see. So one question is a little bit just tactical, is how many messages per second or per minute are we processing roughly? And so for this particular product that I described for the cardboard box making machines, for that one, it's 2,000 sensor values, and those are all measured per second, and that's per machine. So 2,000 values per second per machine. Although in terms of actually sending it over the cellular signal up into the cloud, you can save some of the bandwidth by just passing updates only instead of passing every value every second if it hasn't updated from the previous second. Someone is asking about how did we come to use SageMaker? Yeah, so one of the benefits I would say of SageMaker, there's definitely pros and cons. the whole AWS stack maybe has pros and cons to it, and I know that they definitely purposely try and if you're using some AWS things, want to make you use more AWS things. But the thing that is really easy about it is that it kind of lets you go very quickly from having a trained model to having a endpoint, like a deployed endpoint that you can ping that model with. And even if you're already using containers and Docker, it still handles a lot of the data processing and auto scaling and things like that for you. And so that part's definitely handy. It has a lot of anything from like Python, scikit-learn, or TensorFlow or PyTorch. All of those are kind of already available as containers that you can use. But there are definitely some differences if you're just used to using regular scikit-learn packages. Like for example, the training data that you're using to train a SageMaker model, you can't be passing it in memory the way that you often would in Python. You have to be reading it from S3. So there's a lot of kind of small differences like that. But it definitely makes a lot of the deployment process easier versus doing it kind of by hand and then having to manage all of the rest of the endpoints and everything on your own. I think I might have time for one more. Thinking about for industrial purposes, is it safe when offline or high latency, and how are we tackling that? Yeah, so also because the fact that we're passing data through cellular, this can be something that can come up if there's like a cell signal problem, or even if the device loses connectivity or something like that. And so definitely we're thinking about in a future state of the system having more kind of caching happening on the firmware side of things, so that when we're disconnected, we're able to actually send like a longer window of data that was not sent while disconnected. But one of the nice things about working in these types of industrial settings is that when you're doing greenfield development like this, it's actually like you're making a new capability that really didn't exist at all before. So even though we want to get really high low latency, even just being able to have something that you can look at and like see the data streaming and like see alerts coming up of like, oh, it looks like something is going wrong here, like these numbers look weird. Having that capability versus not having it is a really big difference. And so even if there's a delay of like 5 or 10 seconds or something like that, at least at first it's not as big of a deal, but generally we want to keep the latency as low as possible. I think I'm out of time, so thanks so much again to everyone for attending. And also, of course, thank you to the organizers. I know that it's such a big job putting together a conference like this, and I'm really glad to be here and have such an amazing impression of the Elixir community based off of this. Have a good one.